Hi everyone, welcome to this video on relational databases and normalization. Today we're going to explore how databases are designed to store data efficiently and why normalization is such an important process. By the end of this video, you'll understand how to normalize a database to third normal form, and you'll know why this is so important for maintaining data integrity and efficiency. Let's get started. First, let's talk about relational databases. In a relational database, data is stored in tables, known as relations. Each table represents a single entity, like a person, a product, or in our example, a gym member. Each row in the table represents a single record, like one gym member, and each column represents an attribute, like their name, address, or membership ID. The key rule here is that each table should only contain data related to one entity. This helps keep the database organized and avoids unnecessary complexity. Let's look at an example. Imagine we're designing a database for a gym. The database needs to store information about gym members and the classes they attend. A first attempt at designing this database might use a flat file structure where all the data is stored in one big table. For example, we might have a table with columns like member ID, name, address, class ID, and class name. But this approach has some problems, especially when dealing with many-to-many relationships, which we'll talk about next. In databases, relationships between entities are crucial. In our gym example, the relationship between members and classes is many-to-many. This means one member can attend multiple classes, and one class can have multiple members. If we try to represent this in a single table, we end up with repeating groups of data. For example, if a member attends 3 classes, their name and address would be repeated 3 times. This is inefficient and can lead to data inconsistencies. So how do we solve this? The answer is normalization. Normalization is a process used to organize data in a database efficiently. The goal is to eliminate redundancy, ensure data integrity, and make the database easier to maintain. Normalization happens in 3 stages: first normal form, second normal form, and third normal form. Each stage addresses specific issues in a database design. Let's start with first normal form. A table is in first normal form if it contains no repeating groups and all attributes are atomic, meaning they can't be broken down further. For example, if we have a column for name that stores both first and last names, it's not atomic. Instead, we should split it into 2 columns, first name and last name. This makes it easier to sort and search the data. Let's look at an example to see if a table is in first normal form. Here's a table that stores gym members and the classes they attend. The table has some columns like member ID, name, and multiple columns for class 1, class 2, and class 3. Is this table in first normal form? No, because it contains repeating groups of attributes for classes. To fix this, we need to split the data into multiple tables. Let's see how that works. To resolve the first normal form issue, we create 3 tables. A table for member, table for class, and table for enrollment. The table for member stores member details like member ID and name. Table for class stores class details like class ID and class name. Table for enrollment links members to classes using member ID and class ID. This structure eliminates repeating groups and ensures each table is in first normal form. Now let's talk about foreign keys. A foreign key is a column in one table that links to the primary key in another table. In our gym database, the table enrollment table uses member ID and class ID as foreign keys to link to table member and table class. For example, if we want to find all members enrolled in the Monday Pilates class, we can use these foreign keys to join the tables and retrieve the data. In the table enrollment table, the primary key is a composite key made up of both member ID and class ID. This ensures that each record in the table is unique. For example, the same member can't be enrolled in the same class twice. This is a key concept in database design, especially when dealing with many-to-many relationships. Now, let's move on to second normal form. A table is in second normal form if it is in first normal form and has no partial dependencies. A partial dependency occurs when a non-key attribute depends on only part of a composite key. In our table enrollment table, there are no partial dependencies because all attributes depend on the entire composite key, such as member ID and class ID. So this table is already in second normal form. Let's check if the table enrollment table is in second normal form. Since it has no partial dependencies, it is in second normal form. This means we can move on to the next stage, third normal form. A table is in third normal form if it is in second normal form and has no non-key dependencies. A non-key dependency occurs when an attribute depends on another non-key attribute. For example, in the table class table, if we store the instructor's name along with the class details, the instructor's name depends on the instructor ID, not the class ID. This creates a non-key dependency, which we need to resolve. Let's look at an example. In the table class table, we have columns like class ID, class name, instructor ID, instructor first name, and instructor surname. Here, the instructor's first and last names depend on the instructor ID, not the class ID. This is a non-key dependency. To fix this, we need to create a separate table for instructors. To resolve the non-key dependency, we create a new table called table instructor, which stores details like instructor ID, instructor first name, and instructor surname. Now, the table class table only needs to store the class ID, class name, and instructor ID. This ensures that our database is in third normal form. Now, our database has 4 tables. Table member, which stores member details. Table enrollment links members to classes. Table class, which stores class details. And table instructor, which stores instructor details. This structure ensures that the database is efficient, easy to maintain, and free from redundancy. Let's talk about why normalization is so important. Normalization has several advantages. It makes the database easier to maintain and update. It eliminates unnecessary duplication of data. It ensures data integrity, meaning the data is consistent and accurate. It improves efficiency, making searches faster and reducing storage requirements. Normalization makes databases easier to maintain. For example, if we want to add a new field, like class duration, we only need to update the table class table. This localizes changes and reduces the risk of errors. Normalization ensures data integrity. For example, if an instructor leaves, the database won't allow their record to be deleted if they're still linked to a class. This prevents orphaned data and ensures consistency. Here's another example of data integrity. If a member changes their address, we only need to update the table member table. This ensures that the change is reflected everywhere in the database without any inconsistencies. Before we wrap up, let's review some key questions. How do you normalize relations to third normal form? What properties does a relation in third normal form have? And why are databases normalized? If you can answer these questions, you've mastered the basics of normalization. So to summarize, normalization is a 3-step process that improves database design by eliminating redundancy, ensuring data integrity, and making the database easier to maintain. The 3 stages are first normal form, second normal form, and third normal form, each addressing specific issues in the database structure. So that's it for this video. I hope you now understand how to design and normalize a relational database. Remember, normalization is a key skill for creating efficient and scalable databases. Don't forget to practice with the worksheet, and I'll see you in the next video. Thanks for watching. Bye for now.